There is a place in the mountains of southern Oregon where the water is so clear, so impossibly blue, that early visitors swore it had to be an illusion.
There's a lake in southern Oregon so blue it looks fake in every photograph ever taken of it. And for most of the 20th century, nobody on Earth knew what was sitting at the bottom of it. Not because nobody was curious, because nobody could get there. It was too deep, too cold, and too crushing for a diver to survive. So for decades, the deepest lake in the United States kept its floor completely hidden, a mile-long secret sitting under some of the clearest water on the planet. Then, in the late 1980s, a team of scientists did something nobody had done before. They climbed inside a small submersible, sealed the hatch, and rode the machine straight down into the dark to see it for themselves. What they found down there did not just surprise them. It rewrote what biologists thought they understood about where life can survive. And decades later, that same discovery is helping scientists imagine what might be waiting under the ice of moons hundreds of millions of miles from Earth. To understand why this lake became such an obsession for researchers, you have to understand that Crater Lake was never really a lake to begin with. It started as a mountain. Roughly 7,700 years ago, a peak known today as Mount Mazama stood in this spot, a tall, glacier-covered volcano that had been active for hundreds of thousands of years. Then it erupted in one of the most violent volcanic events North America has seen in the last 10,000 years, blasting so much magma out from underneath itself that the ground could no longer hold up the mountain above it. The summit did not explode outward so much as it collapsed inward, folding down into the emptied chamber beneath it and leaving behind a massive volcanic basin called a caldera. For a while, that basin was just an enormous smoking pit. Then slowly, over the course of centuries, it began to fill, not with rivers, not with streams, carrying runoff down from distant mountains. Crater Lake has no significant inlet and no significant outlet. Every drop of water inside it arrived as rain or snow, falling directly into the caldera year after year until it became the deepest lake in the country, reaching down close to 1,900 feet at its lowest point. That single detail, no rivers in and no rivers out, is the reason Crater Lake looks the way it does. Ordinary lakes are murky because rivers are constantly dumping sediment, minerals, and organic debris into them. Crater Lake never gets that kind of input, so the water inside it is close to what scientists would call optically pure. Sunlight can travel further through it than through almost any other body of fresh water on Earth, which is part of why the lake glows that impossible shade of blue that people drive hours to photograph. But that same purity created a genuine scientific puzzle. If there is barely any organic material flowing into the lake from outside, and if sunlight only reaches so far down before the water goes completely black, then what, if anything, could actually survive on the floor of that basin, 1,900 feet below the surface, in total darkness and near freezing cold? For a long time, the working assumption among researchers was simple. Down there, they figured, was probably close to lifeless, a cold, dark bowl of volcanic silt with nothing much going on. Getting an actual answer to that question took decades, mostly because the technology to reach the bottom of Crater Lake safely simply did not exist yet. Early researchers in the 20th century were still using weighted lines lowered from boats to measure depth, essentially guessing at the shape of the lake floor one sounding at a time. It was not until the 1970s and 1980s that scientists began using sonar and acoustic imaging, something like a CAT scan for the lake bed, to map the basin properly. That mapping turned up something unexpected. Certain patches of the lake floor were giving off far more heat than the surrounding rock, more heat than could be explained by anything except water escaping from deep underground. If that was true, it meant Crater Lake might not be as geologically dead as everyone assumed. The volcano that destroyed itself 7,700 years ago might still be quietly active beneath the water, and the only way to know for certain was to go down and look. That mission fell to a team from Oregon State University, working with the National Park Service and the United States Geological Survey. In 1987, they sent an early remotely operated vehicle down into the basin, a tethered robot with cameras that let them scout the terrain from the surface. What it showed them was promising enough that the following summer, they went a significant step further. They brought in a one-person research submersible called Deep Rover, a small, spherical, clear-hulled vehicle designed to carry a single scientist down to depths that would be lethal in ordinary diving gear. Between 1988 and 1989, researchers including oceanographers Jack Diamond and Robert Collier, along with park biologist Mark Botanica, made a series of dives inside Deep Rover, some lasting up to 8 hours, descending as far as the lake would let them, well past 1,400 feet, and eventually approaching the deepest parts of the basin. Botanica later described what it felt like to be alone in that little acrylic bubble, sinking through water that kept getting darker and colder with every passing minute, watching the readout climb past 600 feet, then 1,000, with nothing outside the hull but blue fading slowly into black. On one dive, at a depth of over 1,900 feet, he looked up through the acrylic dome above him and could still make out a faint trace of light from the surface, a small but striking reminder of just how clear this water really was. But the researchers were not down there for the scenery. They were down there to answer the question that had been nagging at scientists for years. Was the floor of Crater Lake actually empty? Or was something living down in that darkness? The first surprise came sooner than anyone expected, and it did not come from the very bottom of the lake. It came from the moss. Earlier surveys using diverse and simple sampling gear had already found deep water moss growing at depths that seemed almost unbelievable 100 feet, a new world record for how deep a photosynthetic plant had ever been found growing. The species, a type known as Drepanocladus, Aduncus, hung off underwater cliffs in some places and carpeted gentler slopes in others, forming dense beds between roughly 100 and 250 feet down that lined up closely with the zone where the lake's phytoplankton was most productive. Around those moss beds, researchers found a whole miniature ecosystem of algae and diatoms living as epiphytes, essentially tiny hitchhikers clinging to the moss and feeding off the same faint light filtering down from above. It was already a strange find. Crater Lake's water was so clear that plant life could survive at depths where, in almost any other lake on Earth, sunlight would have run out hundreds of feet earlier. But the moss was only the surface story, literally, as Deep Rover kept descending, past the reach of any usable sunlight, into water that stayed just a few degrees above freezing. The researchers expected the biology to essentially stop. Instead, their cameras and lights began picking out patches of color on the lake floor that had no business being there. Yellow and orange mats, some small, some sprawling more than 60 feet across, clinging to rock and sediment in a part of the basin that should have been as close to biologically empty as fresh water gets on this planet. When the scientists examined what they were looking at, they found dense colonies of bacteria, organisms from genera called Gallionella and Leptothrix, that were not living off sunlight or drifting organic debris at all. They were living off chemistry. These bacteria were drawing their energy from minerals dissolved in warm fluid that was slowly seeping up out of the lake floor itself, fluid that had clearly traveled up from somewhere far below the sediment, carrying dissolved iron and other compounds with it. In other words, the volcano that collapsed to create this lake nearly 8,000 years ago had not gone completely silent. It was still leaking warmth and chemistry into the water above it, and an entire community of bacteria had built itself around that leak. Piloting the submersible close enough to study these mats safely was not a simple task. Deep Rover was never designed to sit motionless. Every small adjustment of its thrusters stirred up fine sediment that had been undisturbed for centuries, and the pilots had to learn to approach slowly, easing the vehicle down in careful increments so the very cameras they were using to document the mats did not end up clouding the water around them. Communication with the surface ran through an underwater telephone line, and every dive was tightly bound by the limits of the submersible's life support system, which meant researchers had only a narrow window to record measurements, collect samples, and simply look before they had to start their ascent back toward daylight. Despite those constraints, dive after dive kept turning up the same pattern. Wherever the instruments picked up a spike in heat, the cameras tended to find another patch of that yellow-orange bacterial growth waiting nearby, as if the mats themselves were acting like a visible map of where warm water was escaping from the lake floor. This was the moment the science genuinely shifted. The process these bacteria were using is called chemosynthesis, and it had already been documented in one of the most extreme environments known to science, the hydrothermal vent fields discovered along the mid-ocean ridges of the deep sea, where scalding mineral-rich water pours out of cracks in the ocean floor and supports entire ecosystems that have never seen a single ray of sunlight. Finding a working version of that same chemistry inside a freshwater lake, in a place families visit every summer to take pictures of the shoreline, was not something anyone had expected. It meant the biological rulebook that scientists had built around sunlight-driven food chains had a real exception, sitting inside a mountain in Oregon, not thousands of miles down in the middle of an ocean. The temperature readings the team took only reinforced how unusual this was. Across most of the deep basin, the water hovered right around the freezing point, cold enough that a human without protection would lose consciousness within minutes. But directly around these bacterial mats, instruments recorded water temperatures as high as 66 to 68 degrees Fahrenheit, a difference so extreme in that setting that it functioned almost like an oasis of warmth in an otherwise frozen basin. Alongside the bacterial mats, the researchers also documented something else that had never been seen in the lake before: pockets of strikingly blue, highly saline pools sitting directly on the lake floor, distinct from the fresh water surrounding them, some as wide as 20 to 25 feet across. These pools appeared to be forming where warm mineral-laden water was leaching salts out of the surrounding volcanic rock as it slowly worked its way up from below, creating small, self-contained chemical environments unlike anything documented in a lake of this kind. Put together, the picture that emerged from those dives was almost the exact opposite of what everyone had assumed going in. Rather than a dead, featureless basin, the bottom of Crater Lake turned out to be geologically alive, still venting the leftover heat of the volcano that built it, and biologically alive in a way that depended on that heat rather than on the sun. It also helped explain something locals and park rangers had noticed for generations, but never fully understood. Despite sitting at high elevation and getting buried under enormous amounts of snow every winter, Crater Lake almost never freezes over completely. Researchers had long assumed this was simply a matter of the lake's sheer volume being too large to cool down quickly. But the discovery of warm water steadily seeping up from the lake floor suggested there was more to the story, a slow trickle of geothermal heat rising from the deep basin that may be helping keep the whole system from locking solid, even in the harshest Oregon winters. There is another character in this story that had been sitting in plain sight the entire time, and once the deep dives were finished, it started to look a lot more meaningful. Locals call it the Old Man of the Lake, a full hemlock tree trunk that has been floating upright in Crater Lake for well over a century. Its bleached, weathered top rising several feet above the but once scientists understood what was happening on the lake floor. The old man started to look less like a curiosity and more like a visible piece of a much larger system. Every year, storms knock branches and occasionally whole trees down off the slopes surrounding the caldera, and unlike the stubborn old man, most of that wood eventually becomes waterlogged and sinks, carrying a small deposit of organic carbon down into a basin that otherwise receives almost none. In a lake with no rivers to deliver nutrients from the outside world, occasional sunken timber may be one of the few direct links between the sunlit forest above and the dark, chemistry-driven world below. The story of how this lake came to exist is not only written in rock and sediment either. It also survives in the oral traditions of the Klamath people and related tribes, who have lived in this region for thousands of years and whose ancestors witnessed the eruption of Mount Mazama firsthand. Their traditional accounts describe a great and destructive conflict tied to the mountain, a story passed down across roughly 300 generations long before any written record of the eruption existed. When scientists later studied ash layers and sediment cores pulled from the lake floor, reconstructing the timeline of Mazama's collapse almost layer by layer, the physical evidence lined up with a story that had been carried forward purely through memory and voice for thousands of years. It is one of the clearest examples anywhere in North America of a human community preserving the record of a real geological catastrophe across an almost unimaginable stretch of time, long before geologists ever picked up an instrument to confirm it. None of this makes Crater Lake a finished, fully understood place, and it certainly does not make it an untouched one. In recent decades, non-native crayfish, introduced to parts of the lake in the 20th century, have been gradually spreading into deeper and deeper water, competing with and preying on native species that evolved in this basin without ever needing defenses against them. Researchers monitoring the lake describe the spread as slow but steady, a reminder that even one of the most isolated bodies of water in the country is not sealed off from outside disturbance. At the same time, scientists are still working to understand just how extensive the deep bacterial communities are, how old some of these bacterial and moss colonies might really be, and whether there are additional vents, additional warm pockets, or additional pieces of this ecosystem still waiting to be mapped in parts of the basin nobody has closely examined yet. What makes all of this matter well beyond the borders of one national park in Oregon is the bigger question it forces scientists to sit with. For a long time, one of the central assumptions in the search for life beyond Earth was that liquid water alone was not enough. You also needed sunlight, or at least something close to it, to power a food chain. That assumption runs into a serious problem the moment you start looking at some of the most promising places for life in our own solar system. Icy moons like Jupiter's Europa and Saturn's Enceladus, both of which are believed to hide deep, dark oceans of liquid water underneath miles of ice, oceans that never see a single photon of direct sunlight. If life absolutely required sunlight to get started, those oceans would be non-starters. But chemosynthetic ecosystems, first discovered at deep ocean vents and now confirmed in a much more accessible setting at the bottom of Crater Lake, offer a working example of exactly the opposite. They show that a cold, sunless, pressurized body of water, warmed only by heat rising from below and fed only by the chemistry leaching out of volcanic rock, can still support a functioning ecosystem. That is precisely the kind of environment scientists believe may exist under the ice of those distant moons, and it is part of why researchers who study the potential for life elsewhere in the solar system keep circling back to places like Crater Lake as an accessible, real-world reference point for how such ecosystems might actually work. It is worth being honest about the limits of that comparison, too. Crater Lake is not Europa, and the bacteria living on its floor are not a preview of what an alien organism would actually look like. The value of a place like this to astrobiology is narrower and more practical than that. It gives scientists a real, physically reachable system where they can test instruments, refine the kinds of chemical signatures they should be searching for, and study how a chemosynthetic community actually behaves and spreads across a lake floor, all without needing to leave the planet to do it. That kind of groundwork, quiet and unglamorous as it sounds, is exactly the sort of research that ends up shaping how future missions are designed long before any spacecraft actually leaves Earth. Step back and look at the whole picture, and Crater Lake stops looking like a simple postcard destination and starts looking like something closer to a layered archive. There is the ash and pumice at the bottom recording the exact violence of the day Mount Mazama came apart. There is the oral history of the people who watched it happen and carried that memory forward for thousands of years. There's a floating log that has refused to sink for over a century, quietly marking one small piece of the slow transfer of nutrients from forest to lake floor. And down at the very bottom, in water cold enough to be lethal and dark enough to have gone unseen by any human eye for nearly 8,000 years, there are bacterial mats and deep moss beds running on a completely different set of rules than almost every other ecosystem most of us will ever encounter. A version of life that survives on rock and heat rather than light. Scientists went looking for an empty basin and instead found a working, living system that had simply been waiting in the dark for someone to bring a light down to it. So here is the question worth sitting with after all of that. If one of the most photographed, most visited lakes in the entire country was still hiding an ecosystem like this at its bottom until researchers finally went down and looked, what else is sitting closer than we think, in places we already assumed we understood? Let me know in the comments what you think is still waiting to be found in the dark corners of our own planet, and where you would send the next camera if you could choose.